So thank you, Martin, for the invitation. Thank you all for having come this morning here. Just a question, are there any physicists in the room? Okay, so as always, 10% of us cannot find a decent job, so we end up doing some funny things. Are there librarians in the room? Only 4. Okay, I'm going to pick on you. Is there anybody who wants to hear about this Boson thing, or shall I just skip to the open access part? Boson? Wow! I tell you, that's part of the cool thing. If you would have done this 5 years ago, everybody would have wanted to skip to the open access thing. So, Martin is trying to convince you that I'm qualified to give this talk, but I'm not totally sure about, so I'm trying to explain that I think I'm qualified to give this talk. At the moment, I am head of open access at CERN, and that's, I think, the first talk ever that I give without wearing a tie, but I was told not to wear one. Luckily, I was told not to wear one. And I've not always been head of open access at CERN. In reality, I am a little kid at some of the space age. When I was very little, my parents gave me a globe of the moon. There was a time in which going to the moon was routine, and we were told that when we will grow up and work hard, we could go there on holidays, and we will have a space base on the moon, and we will go to Mars. And of course, this gave me, like I think several others in this room, the bug for science. And eventually, I decided to take the thing in my own hands, and I did train as an experimental physicist. When I still used to have hair and a different dressing style, I worked at the L3 Collider. At the time, this was the largest instrument that we had ever built, and we tried to do many things, among which looking for the Higgs boson 10 years too early. My master thesis, and this has to be a really long time ago, 20 years ago, was about big data. And I was privileged to analyze big data because I was let to play with the single most coolest machine that we had at the time. This had 4 CPUs in one single box, had 112 megabytes of RAM, had 4 gigabytes of disk, so I could put all the data on the disk. And the most important thing of it is that it was so warm. I was doing my master thesis in Geneva in winter. I was coming from the south of Italy. They had like snow on the ground. Wow, I was just hugging the thing. And for how ugly and clunky it might look, there was something, was a very interesting lesson that I learned there and then about big data, was the price tag of big data. The price tag of that thing was exactly to the cent the price tag of this thing. By the time I did my PhD, big data has become easier because big data has become a commodity, and I could use a CERN computer center, which was built starting from IKEA component, because you just put shelves and put a lot of computers on the shelves. This was before people knew how to build computer centers. It was a bit back. Okay, I hope I convinced you that I'm qualified enough to give this talk, and I'll speak about the boson because you wanted to hear about the boson. So, buckle up. We are going to start with some physics. Sorry, that's the wrong one, this one. So, usually this hurts and this pain. But believe me, this pain a lot when you try to know what happens on this side of the universe, and this pains a lot if you try to figure out what happens on this other side of the universe, on the other side before time began. We have this thing, and by now we drill into, I have a little niece, she's 8, and she sort of has already been drilled at this at school. Seems totally normal in our understanding. Oh yes, there was this big explosion, and then slowly the electron formed, and then the quark formed, and then the neutron, the protons, and then the nuclei, and then the atoms, and then suddenly we have galaxies, and everything is so nice, everything is so beautiful, we are so happy. This is very counterintuitive, and some of you who are in science communication know that. Because the kind of counterintuitive thing that we are trying to explain to people is that you have like a big explosion, a firework, something which goes all over the place, and you expect things which have been projected with all the energy that exists as far away as possible to actually moment stop, slow down, coalesce onto each other, and form everything that you have around. This is not very intuitive. And actually, it's not very intuitive also at a physics point of view. And the reason for which this actually can happen is because particles, elementary particles, which then eventually make up the nuclei, the atoms, the galaxies, and everything else, have mass. The reason for which particles have mass sits a tenth of a billionth of a second after this initial explosion, after the Big Bang, something very bizarre happened at the time. There was a ripple, a strange ripple in the fabric of space-time, and something called the Higgs field came into being. At the time it was not called the Higgs field, it has been called the Higgs field later, after Peter Higgs, more on him in a while. Now, how does it happen that particles have mass? So let's use this analogy. Let's imagine that there is a room full of CERN, a cocktail party of scientists, and this is the Higgs field. And suddenly a librarian, I told you of Piccolo, walks through the room trying to connect with a fancy badge with the scientists. Is not receiving much attention. So let's do this again. In this experiment, in this thought experiment, we have something which permeates the entire world, and that's the Higgs field. And when somebody crosses through it and does not interact with the Higgs field, does not acquire any mass. It just goes through and is a massless, poor, lonely librarian. Then something else happens. In the same cocktail party in the CERN cafeteria, please note the likelihood of the physicist here, we have a very important, notorious Nobel Prize physicist who works in the same cocktail party and starts trying to go through the room, and everybody recognizes him. Everybody wants to talk to him. Everybody wants to be advised by him. And then slowly the person tries to make his way through the room to get eventually to the bar and get a pint, but it just can't. It can't and goes very slow because by its interaction field, it has acquired mass. So there is a very funny idea, if we go back for a moment. What I try to posit here is that we have no clue on how things exist in the universe because they have a mass, and we don't know where mass comes from, and we believe that there is a sort of ripple everywhere which gives mass to things. It's a very beautiful idea, and the first thing that we learn about science and science journalism and science communication is that no matter which good idea you have, you should prove that this is right. How do you prove that this is right? You prove it because, and here comes to how science peer review and the scientific discourse happen. It happens when, and this is an interview that Peter Higgs gave at CERN after the announcement of the discovery of Higgs boson 1.5 years ago. He wrote a short paper in 1964, he submitted it to a journal, and it was refused. And he thought that the paper was refused because it was too short. After all, the paper at the time, he said, was only 1 A4 pages, so it was objectively short for today's standard. So he thought he had not spoken enough about physics in his mathematical idea. He said, oh, actually, there is something else. There is some leftover particles which do exist around, and this is eventually what was called the Higgs boson. That's where the first idea came from. So what happens is the following. Take the same cocktail party room of before, and imagine somebody enters the room from outside and gossips. Any gossip, everybody likes gossip, the scientists as well. And the gossip, the people are closer to the entrance to the door, they hear the gossip first, and they cluster to each other to share the gossip and to gossip even more. And then slowly they tell the gossip to somebody who's close to them, and eventually the gossip makes its way through the room. If you look at it, what this looks like is exactly looks like when the famous scientists had walked through the room. So what is happening here is that a vibration in the space-time, a gossip, is creating something which looks like a particle. It looks like something going through. And that's exactly the idea that comes with the Higgs, and that's where the Higgs boson comes from. So the Higgs boson is something which exists as a ripple in our space-time and explains that the idea on how everything has a mass is correct. I will fast forward now, that was enough physics. Part of the idea comes from Peter Higgs. A similar idea in parallel came from François Englert and Robert Brout, who passed away in 2011, and Higgs and Englert shared this year Nobel Prize. And in parallel, another group of Kebo, Garonek, and Hagen had a similar idea. By the way, this happened to be called the Higgs boson, and now we have settled that the mechanism is called the Higgs-Englert-Brout mechanism. By the way, the B of boson, if you give this talk in India, is a capital B, because a boson is a particle called after Bose, which describes how these particles, the statistic of this particle looks like. There are other unfortunate ways where science communicators have contributed to call this particle. And there is a story, if you read the book of Lederman, who tried to look for Higgs boson in the States for many years. In reality, it's all the publisher's fault. After all, I mean, head of open access, I have to say that it's always the publisher fault. It was never the publisher fault. Actually, the publisher wouldn't let it call the goddamn particle, his book about having looked for the Higgs in the 80s. That's why it was just shortened to the God particle. So that's the paper of Peter Higgs, which was at the end of 1.5 pages, and this was 1964. And I've told you about the boson, and 1964 happens to be 50 years ago. That's a long time. Why it has taken us such a long time to find this particle, and what do we learn about the way science is made, and about the way we have to overcome scientific challenges when they are exactly at the very edge of our understanding of the universe? How do you actually look for the Higgs boson? As I told you, something happens at 10 to the minus 10 seconds, a tenth of a billionth of a second after the Big Bang. So we are somewhere here now. So what you do to look for the Higgs boson is just to go back in time and go up in energy to reproduce the way the universe looked at the time. Of course, you cannot create another universe to look at that. You have to do your very small, fancy little one. And then that's what you do in a collider. And what you try to do is to say, fine, if I put enough energy in this place, do I see something coming out which existed at the time, which is Higgs boson? That's what my organization does, CERN, European Organization for Nuclear Research. And this is not only a story of CERN as a facilitator, as the place where the infrastructure exists, is a story of over 10,000 scientists that over 20 years, hailing from 85 different countries, have built the LHC. The LHC is, I think, everybody by now, and we are very lucky to have been so exposed to science communication and to the media. The LHC is in the underground, in a 27-kilometer tunnel below the Geneva and French countryside. It is, the superlatives are not sufficient. You can use all the superlatives you want. It's the largest scientific instrument ever built. It's the one that took us the longest to build. It's the coldest thing from here to outer space. It's the place where we have particles going at 99 point, all the 90 want of the speed of light. These particles collide in a single place, and in this single place you have detectors. Detectors are these enormous big digital cameras. The size of a person is about, this is the size of a person. And what they are enormous. They are, the talk is not adapted for London, they are as big as a cathedral, and they are as heavy as a large pile of steel. And what they are exactly a big digital camera, literally. Each of those detectors contain 100 million sensors, which take 40 million pictures every second. And then you look at these pictures, and they look like this. It's not very fascinating. And the point of big data, the point of this kind of big data, is that almost all the data that you take looks like that. It's useless. You just throw it away. So out of the 40 million images, events that we collect at every single second over 4 detectors, we just throw away almost everything, and we keep just a few hundred. And by the way, some people have been inspired by the fact that it looks like a lot of bricks, and it looks like Lego bricks, and they build their own Lego atlas. If you follow the link, you can get the instruction to build a particle detector with Lego bricks. So looking for the Higgs is very hard, because the largest amount of stuff that you get, it all looks like that, and in reality you are looking for something which is very special, unique. What you're looking for is a special snowflake in a snowstorm against a snow field. So you have billions, billions, and billions of events, where there are just a few which are the ones which you are interested in. Again, this comes back to big data. That's actually as big as it gets. Just the first 2 years of data of the LHC, which underpins the discovery of the Higgs, we are going to get much more data as of the restart of the machine in 2015, is 100 petabyte, which is 100,000 terabyte, which is what we have on tape at CERN. Now I've been at CERN like 20 years, and when I arrived, 4 gig of disk, that was really the cutting edge. So you can really understand how we had to surf exactly the really cutting edge of technology to be able to deliver this kind of science. And you cannot analyze this data on your desktop, or let alone in a computer center, the way this data is analyzed is on the grid. So what happens is that we have 8 large computer centers which are interconnected around the world, and they might host the data you need or not. So from your desktop you request a part of analysis to be done on some data. This part of analysis is shipped out over all these data centers that ship to each other the pieces of data which are needed to deliver to you the result. There is a very nice app. It looks like the flight path across the Atlantic on a Sunday. It's actually in real time you can see the packets of data that move around. And there is at every single moment a traffic of several terabytes. We have these lines which go up to 100 gigabit, and we have tested at terabit. More than a fit of technology, there's a fit of collaboration. You have to imagine what it takes to have 10,000 scientists and engineers, which are all right, to work together over such a long period of time. You need to install and maintain the hardware which is used. You have to go through things which are, imagine what it means to cable 100 million sensors and actually cable the right ones with each other. The machine runs 24 hours a day for several months a year, and this has to be, the shifts have to be taken. Can you imagine the amounts of millions of lines of code which underpin the processing of the data and the analysis of the data? Imagine the amount of discussion, a conversation to form a scientific consensus, because at the end there is only one scientific truth, even though there are 10,000 people looking at it at the same time. And after more discussion, the intellectual adventure ends up to things which are too geeky even for this audience. That's the Higgs. It looks better like this, that's the one they usually we show to the press. And it looks better than the big pile of Lego bricks that we saw before. The rest, again, is a very interesting cooperation of science outreach and communication and physics per se. CERN has decided to do in a very open way over the last years the search of the Higgs boson, which means taking data and doing scientific seminars with the press, with the media, and often with several hundreds of journalists in the room. This has paid off in a way, in the sense that everybody in the room here wanted to know what the boson was. Everybody was curious about this. Everybody knew what the LHC was. I can tell you 10 years ago it wasn't like that. And on 4th of July 2012, the announcement of the discovery of the Higgs took place at CERN. This is the moment in which our Director General in the center summarized the findings of the 2 separate experiments to say that he thought that we had it. And that's a picture which we are particularly fond of, because it signifies continued investment in science. These are 1, 2, 3, and 4 previous Director Generals of CERN. The mandate of a Director General is 5 years, who have overseen the construction of the LHC machine. That was a LHC project period. You understand that without a continuous and sustained investment in science over a timeline which is not the mandate of a government, by his 20, 30 years, you cannot get to a point where you can have this level of discoveries and this level of collaboration. This was in the centerpiece of the New York Times, and this is Peter Higgs visibly happy at the moment of the announcement. That's just a still. On 1 month ago at CERN, in the big building where all physicists are, everybody was looking at a TV screen, which is up here. It wasn't a football match, but at the moment in which this thing went up on the screen, the excitement was the one of a football match. I spoke about the boson, I spoke about the 50 years, I spoke about the 3 scientists in the 50,003. What I would like to do is to draw some lessons on the way this global scientific collaboration helps us driving some innovation in the way you communicate among scientists, and the lessons through which some open access initiatives can actually accelerate the way this science is made, a bit along the line of what Martin said in his introduction. To do this, I would like to go back to the article. That's the Higgs article. It's an article. It looks like an article. It's very boring. In 1964, everything was so boring. People just wrote articles and put them in a paper. We all go better. So that in 2012, when we found the Higgs at CERN, we actually wrote an article and put it in a paper, in a journal. It's the same. But it's not totally the same. It's not totally the same because the kind of disruptive, the seeds of disruption in the way scientists communicate and cooperate in our field, they are around since very long, and traditionally there have been several seeds of this disruption which has led the way to some forms of open access and to some forms of acceleration of communication. That is where I would like to stress the rest of my conversation this morning. To demonstrate that actually these seeds of disruption which builds on a tradition, the tradition of the paper, the tradition of the citation, the tradition of the author, eventually results in a disruptive tradition as many innovations come from this field. I go back to the paper. That's very boring. Let's zoom down to the corner of the paper. One first thing that we find is that who can sign a copyright transfer form if you have 3,000 authors on a paper? This is a very interesting question. I can tell you, it's all, being a lawyer at CERN is cool because you have to answer these kind of questions as well. CERN retains the copyright for, on behalf of these large experiments. Who is the author of such a large paper? But there is a corporate author. There is the CMS Publication Committee chair. So you have a very organized machine on how a paper is written, is submitted, and so on. The paper was published, this particular paper was published in Elsevier Journal, but our papers are published in American Physical Society, Springer, Elsevier, IoT, in all journals from all publishers in this field. The paper was published under CC BY, and actually one of the first articles published by Elsevier under CC BY have been the articles coming from CERN. So you can see some sign of small disruption, which is built on top of something which is very traditional, a paper. That's actually the paper. And I can tell you, since I've been looking for the Higgs boson 10 years ago, I know that this small greenish bump, which is there, means that the Higgs is really there. I don't need to read all the rest of the paper. But there are a few things I would like you to look at the rest of the paper, just if you look at that from there without reading it, and it's the fact that there are, half of the paper is article and references. And the other half is something else. The other half are the 3,000 that almost are authors in this field. Now, that's disruption in the way you do science, in the sense that what does it mean to be an author on such paper? Actually, what even means to be recognized, identified, and to get attribution of this paper. And what in the Scientific Information Service at CERN, where I work, we have been doing together with colleagues across other laboratories, is to make sure that we have, this is just a snapshot of line 7,100 to 7,145. For every single author in these articles, we have their full name, their surname, the collaboration, the institution, their own ID in Inspire, our system, plus their ID in the CERN Computer Center. This seems what everybody should do now. That's actually what we are doing now. The point is that when we had to solve this problem, which was like 5 years ago, there was no ORCID yet. So we are facing exactly all the problems of attribution and all the problems of communication just before they come. And before they come. There is some wave noise. Very soothing. Let me go back to the paper. Let me go back to the paper again. Let's zoom. Instead of zooming on the fine prints, because nobody reads the fine prints, let's zoom up here at the article information. If I zoom on the article information, I see something interesting as the history of the article. So articles, both articles, there were two because there were two collaborations, right? Both articles had been received on the 31st of July 2012 and published eventually on the, accepted on the 11th of August 2012, accepted the same day. This was available online on the 18th, this is on the 14th, because somebody didn't check the proofs over the weekend or something. I don't know, that's a joke. So there has been a period of time in which this article, in principle, was in limbo. So we have discovered in Higgs, we did a seminar on the 4th of July, the article was submitted on the 31st of July, but you couldn't read it to the 18th of August. It's open access, so it's online, you can see it. No, the article was not in limbo, because in the very same moment in which the article was sent to a journal, both the articles appeared on archive.org. Who does not know archive.org? Okay, 3 or 5, 6, in 3 minutes it will be done. It's a website where you put papers before they come online in a journal. So these articles were appearing open access in a journal. It's not news to this community. And before even appearing open access in a journal, the very same day in which they were sent to a journal, they were posted online in a place used by scientists to exchange information. I would like now to elaborate on what does it mean to put a paper somewhere in our field, and what does it mean to publish an article in our field. Now, in the field of high energy physics, CERN is a large player in the sense that we have often the attention of the press and the attention of the media, whereas on the other hand, our scientific output is only a drop in the big bucket of this field. In this field of high energy physics, there are about 7,500 articles a year. The vast majority of these, 90%, have 1, 2, or 3 authors, like every other article in every other discipline that you are interested in the life sciences and in other fields. Only 2% come from us. So the largest amount of information is produced in our field, mostly by theoretical high-energy physicists who just need a blackboard and chalk, so cheaper to keep. And let me tell you now a story on how the need of theoretical high-energy physicists to communicate their ideas to each other promptly, when there was no fancy clicking badge and no Twitter and no Facebook and no internet, has put the seed of a traditional disruption which has led us to an open access infrastructure. Because, I mean, this year we celebrate 50 years of open access at CERN. 50. I know many of you didn't think of open access 50 years ago, maybe 10 years ago, a few persons that I recognize in the room started thinking about open access, but 50 is a long time. So, after the war, the Second World War, that is, more and more governments started paying attention to high energy physics. We have an original sin in the sense that high energy physics is a close relative of nuclear physics, and after the war, every government, after the Manhattan Project, started paying attention to physics to say, well, that's an engine of growth, an engine of discovery, an engine of everything, but there are obvious reasons for which governments wanted to have physics programs. Physics programs meant that there were a lot of physics groups, mostly in the Western world, collaborating with each other. And the issue when you collaborate, when the fastest thing that you have is airmail, because there was no fax either, is a highly non-trivial question. You would like to explain your results and your idea to somebody. The field was booming. Suddenly we multiplied by factors of 10 the amount of people and the amount of machines that do physics. So how do you communicate fast when the fastest thing you have is airmail? With airmail. So people use it to write papers. Once they've written a paper, they would take multiple copies of it. Actually, the cyclostyle was a key instrument. And they would do one thing once the paper was finished. They would send a copy to a journal who would send it through a peer review service. And like in the case of Peter Higgs, maybe asking for a modification, which eventually resulted in the invention of Higgs boson. And other copies, they would actually be sent to libraries all over the world. So you have one official version which eventually goes to a journal which becomes the version of record, and you have another version which is the manuscript of the author, the preprint, which is sent to libraries all over the place. That's the CERN library. These chairs and the tables we still have. This person we still have. we have moved these on, this is 1957, I think once I zoom in there. We moved the desk away, but it's miraculously unchanged. The only thing which has changed is that we don't have the preprint rack here. This would be the place where every Tuesday you will put out the papers which people have sent to CERN, because everybody wants CERN to read the papers that they have written. And you would know what would be new. Mind you, you would know it as soon as the email was arriving from the scientist. If you had to wait and read it in the journals which are there, you had to wait for the paper to go across the world to somebody who would review it. Actually, no, send it to a reviewer across the world, and then send it back again. And then after this conversation was finished, not via email, 2 weeks every time for the letter to go back and forth, you actually print and put on a ship the journals, and then eventually they would go on a library, go on the field, on the wall and read them. So the fact of sending a letter with the information to each other was shaving off like a year or two the scientific process. If you have a field which is booming, you cannot wait 2 years to know whether your idea is good or not when somebody is building an accelerator on the other side of the planet to check if your idea is valid. What libraries were doing, where they were getting the preprints, the CERN library and the library of Stanford, was to do what they were doing with every other material. They were actually cataloging them, like that's the name of the, that's a preprint MIT LNS, Laboratory of Nuclear Sciences, TF, whatever is under there, 26. This is some other information and keywords. This is the abstract. So, in brief, this was the first open access repository ever. That actually is still there. That's truly yours in the CERN Open Access Repository. These are all the preprints that we have received over 45 years. We stopped receiving them around the year 2000. And they're still all there. The card catalog is still there. You can look for a preprint, go open and pull this out. Card catalog eventually put it online. There is one interesting thing that is part of an open access infrastructure where information flows freely and is annotated by others who are not the producers. Some libraries who were receiving the preprints at the time would look at them and would try to disambiguate the authors. They would do some semantic markup to say, oh, this is a paper about this subject, and actually this is a paper presented at this conference, and we have the announcement of this conference, and actually we have other papers which have been presented at this conference, and so on and so forth. And one key idea that Stanford had was to put all this information in an index and put the index on a computer. If you go to Cupertino, just a stone throw from Apple, there is the Computer History Museum, and the very first library catalog is there, because that's the computer out of which the SPIRES service was run at Stanford. Sending all this stuff via email, via paper mail, is not very efficient, but it's the only thing you can do, because email was not pervasive and ubiquitous, even in the academic community, till the early 90s. In the early 90s, Paul Ginsberg and Los Alamos had an idea, which is to say, instead of sending all these papers to each other, with the strange effect that if you are important, everybody sends you their stuff because they want you to read it. And if you are nobody, nobody sends you their stuff because why would they want you to read it? Can we just do a listserv where everybody sends something on the listserv and they get something back? It sounds very bizarre, but in 1991 there was no value. So the best you could do was to run a listserv. And this is where Archive as a system was born, a place where you would mail your, email your paper in LaTeX, and then you would get a digest back with all the abstracts. Then you would send an email back to say, I want this one, send it back to me. You will get the LaTeX back, then you will compile it and see it. That's roughly when I started in the discipline, so as you see, I'm conversant on how to use this system. Something else happened that you might have heard of. Does everybody know? So I think everybody knows which was the first website, right? info.cern.ch and was a CERN. Does everybody know who was the first website out of Europe? There's a usually test of your age when you say very continuous. The first website out of Europe was the browsing interface to the thing in the Computer History Museum, which meanwhile is moving on another system. The first website in the US was spires at Stanford, and was put up just for one reason, to let people from any place in the world browse the catalog of all the preliminary publications which existed in this field. That's the original email that Tim Berners-Lee sent in December 91 to alert people that this thing existed. Now it looks a bit better. We run it all together, the four large laboratory in the field, and I have this weight on my shoulder that I have to usually fix the next direction of this thing. And Inspire now is a digital library which has 1 million records, 500,000 open access articles, we have 20 million citation triples, and we have about 20,000 disambiguated authors. It's something which is very fast, like compared to the Computer History Museum, everything is faster. It's something which is very clean, and this is something I wanted to get when it comes to the value of abstracting and indexing services today, and the value of places where you can go and find all information you want today, and what serves best in the interest of scientists. That's one of the last things I want to say. One thing that we strive to do is to select every single day, every article which exists in this field, either because it's submitted on archive or because it's in a journal, which is relevant to the scientists in this field, and therefore we have a system which at once is clean and is complete. I have also screenshots, it looks like any other digital library. One thing which is interesting is that it's used by virtually everybody in our field. With 50,000 users, we have about 2 searches per second, which for those of you who run the IT infrastructure or publishing company is very little, but for those of us who run services which are run out of libraries and are small scale is a lot. Then you can do funny things with this, because this is the volume of searches in Inspire as the time in the visitor browser. So we know that physicists are working between 7 and 8 a.m. They take a lunch break around midday. Most physicists take a break in the afternoon. And then they continue. And they continue. And on average around 2 a.m. they give up. Actually nobody knew that the physicists used to eat. Another thing which I find funny, and again, this is interesting because once you see what people are doing with the power of big data or small data analytics, they are important in the way you deliver a service. This is how much time people spend on the site. That's something that I always have trouble explaining to consultants, because they say, but this is appalling. So your average user is out of the site in 10 seconds. Yes, that's good. We wish they are out of the site as fast as possible, because they come to look for a paper, they find it, they go to they read it. And then we are very puzzled of what people who spend 15 minutes and more on the site do. What do you think they do?
Go and got a cup of tea.
Go get a cup of tea. No, this is active use, it's not the session. They are clean. Somebody who spends 15 minutes on a digital library, what do they do?
Scrapers.
Scrapers? No? Almost? Yeah, almost. They do what everybody does. Never gazing. They look for themselves. They look at all their papers, and our single most successful service is something when we show you the citation logs. So these are all your papers, all your citations, and we tell you that we have added yesterday a citation to this paper of yours by this guy here, because in this way you know exactly when somebody cited you. And if we don't add it, we get a ticket. So basically you see that within usually 7 hours of a paper appearing on archive besides somebody, if we have not captured the citation and +1 in the author pages and the author profile, and +1 if needed on the H factors, somebody will complain very bitterly. Now if you have 50,000 users, you have a few hundred papers a year, a day, each with 20 or 30 citations, you have to capture 3,000, 4,000, 5,000 citations a day. If you miss one, you get somebody complaining. Multiplied by how many days are in a year, and you better have very good machines to do text mining. It looks ugly, by the way. We are trying very hard to reproduce this nice, cozy 1993, 1997 feeling. It's tough because the system that we have below actually is like that. Has altmetrics out of the box and has nice look and feel, and we have to tweak it to look it like that. Otherwise people will complain, will say, you have got just a bunch of young geeks to run the system, I want my old system. So, what we have is an infrastructure in our field where we have people who go and put their papers on archive, and then digital libraries run by the community enrich them and make them findable. We run a survey, this is not high energy physics, it's like social science. We ran a survey where about 10% of the community answered 5 years ago, and we asked them, well, you need to find a paper, where do you go? About 0.1% goes to Web of Science or Scopus. About 10% goes to Google or Google Scholar. We expose everything to Scholar. And 90% goes to this combination of these systems that we run. So I call it the green Pac-Man eating Google. scooping Google in with the civil services. There is something interesting. If you then take the peer-reviewed journals in our field, peer-reviewed journals in our field are, this is the fraction of the content, which is also available free online before publication. And this was only 10% in '92. It was in '96, 80%. As of 10 years back, in the last 10 years, almost 100% of the literature of the discipline has been available for free open access well before publication. The question is, why? Why do people do so? People do so because we have all this citation counted. That's a study we have done, and this is the amount of citation that articles in our field get. These are the citation profile of articles which are just published. So you publish an article, after about 6 months somebody discovers it, they cite it, and they cite it a bit less, and eventually goes to die with all articles. Articles in our field which are appearing free, online, on archive, green, open access before the publication, they are this green line up there. Not only they get 5 times more citations, but they start getting citation 1 year before they are actually published. That's the publication line, the publication time on the journal. So what happens is that the fact that you can read something and cite it has 2 effects in the open. The first one is that, of course, you want to be there, you want to be seen, you want to be cited, so you're going to put your papers out there for everybody to see and to reuse. The second effect, which is the most interesting one, if on average articles are cited 1 year before publication, it means that we've shaved 1 year off the time it takes for an idea to be read, heard, built on, and processed. So by the fact that this discipline needed at the time of airmail a way to talk to each other, and they've kept talking to each other outside of the normal process of peer review and the normal process of journal publishing, you are this discipline works 1 year faster than it would not have done otherwise. You multiply this by the 20,000 people which are around the field, and you have generated thousands of scientists, FTEs, out of nothing, just because you have a way to fastly communicate. I don't have much time left. I just want to say that publishing still means a lot in this field. You have seen the Higgs papers have been published. What it means is a quality assurance service, which for us is important, like for every other field. And today is my day off, Scott Tracy, so I'm not going to talk about that, but that's the way we are trying to convert to open access the entire field. I wanted to talk about open data, but I don't think I have the time, so I think I jump a bit and I will conclude with a couple of observations that we have had in our field. Now, we have a privileged access point in which we can see physicists cooperating on a scale science usually does not cooperate at, and we can see people trying to go around the technology, not the IT technology to do the big data, but just the communication infrastructure to try to find a way to bring ideas to each other faster and better. And the 3 things that we have discovered while creating infrastructure to facilitate this, including now starting having open data, is very often you have very interesting idea, Scientists do not like to be disrupted. Scientists are very traditional guys. A few of us in the room have a science background. You want to do your science. Do you not want to play with gadgets? That you do in your spare time. So every innovation should be, every disruptive innovation that we have seen emerging automatically, we have brought with my team ahead, has been an incremental innovation which is built on a metaphor, which is the metaphor of the paper, which is something which is very traditional, and then something more on top of that. Because this is what the community expected as a service. And working together with the community, we have eventually created the infrastructures which have helped scientists do what they eventually like to do, which is just to share and to communicate. I rather 110 slides, but I think I stupid.